that, thank you for coming to the mathematical and model-based approaches to defense acquisition planning. Our first speaker today is Nikolai Lipscomb, a research staff member at IDA. He is part of the Sustainment Group within the Operational Evaluation Division, focusing on tasks for the Naval Supply Systems Command. Prior to IDA, Nikolai was a PhD student at the University of North Carolina at Chapel Hill, where he received his doctorate from the Department of Statistics and Operations Research. His areas of research interest are optimization, supply networks, stochastic systems, and decision problems. He will be presenting a mathematical approach to wholesale planning.
All right, thank you for coming, everyone. So this is joint work, as mentioned, in the Sustainment Group that I've been working with Dr. Carl Remley and Dr. Benjamin Ashwell, also of IDA. So let's talk about this mathematical approach to wholesale planning. As mentioned, we're in the Sustainment Group. So what is sustainment? Well, we've defined it in textbook definition style. Sustainment is the art and science of ensuring that the department's weapon systems can accomplish their missions. So very simply, the role of, in sustainment, we look at several different aspects of addressing that problem. I'm looking particularly at wholesale, and wholesale market is basically making sure that we have the right parts on the shelf in order to support the department's systems. So if you kind of look at the image that I have on the PowerPoint, think of wholesale as kind of that, that stock shelf in the center. And on the right, you might have the contractors, the repair depots that provide the shelves with the parts. And then you have the war fighters on the left that are requisitioning new parts as the weapon systems, break and need replacements. So material commands are generally in charge of stocking these shelves, and they run these things called working capital funds that essentially, to be, insulated from the yearly appropriations cycle. They have this pot of money that just kind of, perpetually continues year to year, and they use that to, address their sparing needs. So when it comes to sparing, obviously you want to have a well-stocked shelf, but stocking a shelf can cost a lot of money, especially if you want to fully stock it. You can think of it like a grocery store. You might want to try to anticipate the needs of the warfighters as best as you can. This is complicated because lead times for items are often measured in the years. So even if you're putting in, this tactical module or whatever broke down, but you can repair it, but even the repair might take 1 to 2 years to get around. So if you just wait until the thing breaks down for you to put in your order, you're waiting that full lead time, which really hurts the readiness goals of our warfighters. So that's one of the issues is this kind of pre-planning problem. Another thing that material commands need to do is they need to cover their own operating costs. This is typically done, so they are of course paying contractors, repair depots for their repairs, and then they also have to pay salaries, associated logistics costs of their own employees and servicemen and women. So they need to sell these items to the warfighters at a slight markup. So for all intents and purposes, I'm going to use the word profit, but keep in mind that these aren't for-profit institutes, right? They are simply trying to cover their own operating costs and also be able to continue the service into the future to meet readiness goals. So as you can see, this is a complicated problem. Balancing, stocking needs. Can't buy everything, right? Or else you'll run out of money. So anticipating stock while basically handling your budget appropriately is a difficult problem. So there's several ways to approach it. Here at IDA, we've been working on an approach using mathematical programming. It's basically using an optimization framework, which I will talk about in a little bit of detail, to balance these two competing objectives. So how do things work right now? So, right now, obviously, have some sort of committee, people making the decisions on what should we order to stock our shelves. They'll obviously use a lot of data. They know their budgets. They know how much repairable stock is available to send in for repairs. They know, how many back orders there are, what's due, and things like that. And, a bunch of people can make good informed decisions about what to get. But keep in mind, whenever you have people making decisions, there is going to be a little bit of randomness involved. People deliberate and reach different conclusions, no matter what, essentially. Also, keep in mind that the massive size of the scale, sometimes you're dealing with material commands that support hundreds of thousands of items, sometimes millions. So keep in mind that, no matter how many, if you have too many people, then it can get very convoluted. And if you have too few people, it's very difficult for them to make decisions on such a large scale. So the goal of this optimizer, so to speak, was to really provide some sort of initial recommendation that looks at the big picture. It takes in all this entire wholesale state, this entire data universe for the material command, and come up, with some rules that provide ordering recommendations. Why do I say ordering recommendations? I'm kind of on the line of thought that we shouldn't have AI, make decisions for us. We really need to have people kind of vetting things. That's kind of the last sanity check, so to speak. So the idea is that, the optimizers fed a lot of data, but it might not be aware of something like an obsolescence change. For example, a certain platform might be, being decommissioned the following year. And, the optimizer says, well, we should buy 20. Someone might object to that and be like, no, we need significantly less because demands are going to be very low. Similarly, if an op tempo is changing, right, that's going to affect demand patterns, because if you're going, for example, from peacetime to wartime, that is going to affect failure rates because you're using the weapon systems more, and you simply want to adjust your demand projections due to that. So the optimizer, it follows I'm going to define what we call a policy. We'll talk about the idea of comparing policies in a moment. But the idea is that, policy is simply a repeatable, again, keyword being repeatable set of logical rules. So if you feed in one wholesale state, there's no randomness. You're going to get basically ordering recommendations that aren't going to change due to any debate or so forth. The debate can happen after the recommendations. So what do ordering recommendations look like? Very simply, kind of like a grocery shopping list, right? So you have, what items should we get? Obviously, I went with some very fictionalized item names, but it simply says, how many do we need to repair? How many do we need to procure? And sort of the expected costs associated with that. And that's very, obviously, very simple to work with. And keep in mind that this shopping list, or buy list, as we call it, is the result of a policy, or optimizer policy. So IDA, regarding policies, we have more than just the optimizer. We have some other what we'll call heuristic policies that follow, some sort of simple logic for determining their contracting or ordering decisions. So the idea is that, how do we compare, which policy is better than another one? We don't want to just, mysteriously implement this policy and just see how well it performs. That could, be very adverse. So what we do is, IDA developed this package called Wholesale, so Wholesale Simulator. And we can basically, look at sample policies, and, we can do things like replay history, or we can, project possible futures and examine how these policies might perform from, different perspectives. One possibility is to look at, how well do we do with respect to finances? So you might imagine, maybe the line on the bottom in the red, is not doing as well, is not doing too great from a profit perspective. But that same policy might do well from a backorder perspective. So one thing you keep in mind is that, kind of profit and backorder, as I mentioned before, are often slightly competing objectives, in the sense that, usually if you spend a lot, on spares, you're addressing a lot of backorders, but not all of them will sell. So you're kind of in the red due to having bought too many things, and vice versa. So we can replay history, we can, simulate potential futures. Doing that, we can look at policies, and again, this is where we like to simulate, potential different possibilities for the future. We can, produce multiple, as I call them, sample paths on that, or different plays of a potential future based on different demand signals, different lead times, and so forth. And we can produce basically a smattering of data and we can use to produce confidence regions. In this case, we did a two-dimensional confidence regions. I like to look at how we did financially versus how we did relative to back orders. And as I mentioned, IDA has developed a bunch of heuristic methods. The heuristic methods have been in development for quite a while now. Actually, our best heuristic method is quite well performing. And then we have our optimizer, which is, I would say still in its infancy, but it is already, basically on par with the best heuristic method. I expect it to, be performing excellent in the future. One thing to keep in mind is, why do I say they're performing comparably? Well, this red ellipse is kind of the confidence region for the optimizer, and we can see that it's kind of winning the backorder game, right? Who's winning the profit game? The heuristic method, but it really comes to the question of what's more valuable. Do we want to pay so many $1 million to reduce back orders by another 1,000 or so? Who knows? So I might argue which one you prefer is really a subjective choice. And you can imagine something like a Pareto optimality curve. I'm trying to draw it with my mouse, and I notice I don't think the mouse shows on the presenter screen. But you might imagine there's kind of this kind of elbow. Often you use the term elbow of the curve or knee of the curve, which is kind of like where you like to be on Pareto distributions, or not Pareto distributions, Pareto efficient frontiers or optimality curves. So we have the strong performing optimizer method. Let's talk a little bit about the mechanics. So as I mentioned at the very beginning of the talk, it's a mathematical programming method. So mathematical programming, often we have objective functions and constraints. Let's talk a little bit about the objective function. So the objective function considers minimizing back orders or maximizing profit. These are kind of those two conflicting objectives. We have this lever, I'm going to call it gamma. This gamma lever, which we can tune to be, more favorable to one objective over the other. The idea is that we can pick a value. We could pick, for example, 1 or 0 to completely prioritize one over the other, or we could pick something in between. An expert could, of course, make this decision, but we take more of a machine learning type approach, and we train it off of historical data in order to pick an optimal gamma. So this is kind of like a hyperparameter tuning process for those of you familiar. Now I spoke of constraints, just to give you an idea of the flavor of constraints. You don't need to read through all of them, but we have some very simple constraints, such as we need to making sure we're obeying our budgets, right? We cannot order more repairs than we have carcasses available for repair. And then we have slightly more complex constraints, things that incorporate the variability of demand signals, for example. So whether an item is forecastable or not tells us, how easily are we able to predict whether there's going to be a demand and how much of a demand we are expecting. So we use a sequence of linear programs. This ended up being a very computationally efficient method. One of the alternatives was integer programming. Those of you familiar with integer programming might argue that an integer program is just a sequence of linear programs as well. But this is a fixed sequence of linear programs, not an exponential number of linear programs. So it's broken up, linear programs really fall into the two central boxes, but the basic flow is resolve your back orders first, then you do the optimization for repairs and procurements for forecastable items, and then we do repairs and procurements for non-forecastable items. And then there's a little bit of post-processing at the end. The main thing with the post-processing is that since we're using linear programming, that allows you to order 3.1459 nuclear reactors or whatever, which you obviously can't do. It needs to be integer valued. So we have some post-processing to ensure that we have integer orders at the end of everything. I will say that I mentioned this gamma objective tuning parameter. We have another pair of parameters that we tune, lambda and rho. These are in the constraints of the mathematical programs. One way to think of them is that for forecastable items, you're very likely to predict their demand correctly, from month to month. But the question is, you know, how much is too much to buy of a highly predictable item. There should be some limit. That's kind of the way I like to interpret lambda. And similarly for rho, that's the same thing, but for non-forecastable items, you'd probably set a lower ceiling for how many you buy for unlikely items. And that's generally what we see. So again, these values can be picked. Honestly, we have found that subject matter experts often pick, about what we find using the machine learning approach, which, is nice validation for everyone. But what we did was we used historical data in order to determine these values. So how do we do that? So again, we do something similar to, a grid search for those of you who use certain machine learning packages. So let's kind of imagine, we can create a bunch of different parameter values. Pretend we only have one parameter. Maybe we've fixed all but one parameter, and we vary that one parameter and look at the, the performance relative to changing that one parameter. Each parameter value gives us a single point. And as we shift it around, we kind of trace this Pareto optimality curve. So you might have something, what's the best point? Again, I think that's very subjective. But if we look at this graph, there are points that we would probably want to avoid. For example, the point in the very top right is very, profit focused, but the back orders that you remain with are very, very high. That's probably an unacceptable readiness risk. Similarly, you can go super low with the back orders on, the bottom left. That's really, really hurting your profit for not much of a gain, relative to higher values of profit. So perhaps something we might like is, along, the two circle dots. Which one is better? Really, it would probably vary from person to person. And that was kind of like that idea I was talking about. Which do we prefer, the optimizer, the heuristic? They were more or less on the same curve. Just to give you a flavor of, what things look like, I bumped it up to 2 parameters. All I did was I allowed gamma to vary, and then I fixed lambda to be a multiple of rho. So that way, as I change rho, lambda is changing with it. So this is really just a 2-parameter case. But this already shows you that, the dots end up all over the place as opposed to just one Pareto optimality curve when you have multiple hyperparameters. So, what's best here? Well, I might argue, something like that is the best. So one rule, for picking it might be maybe the material command want a specific minimum profit. And they're like, we need this minimum profit. What's the best you can do within that threshold? So that might, be one way to pick a certain point on this graph. But again, it is very subjective. So all we are really doing is presenting, risk trade-offs here. So as I mentioned, so that's the hyperparameter tuning process. I will mention that for linear programs, as discussed before, decision variables are continuous, right? So we end up with orders that are on a continuum, right? So we can't have fractional orders, right? So the post-processing is very simple. You want to order all items according to some sort of priority scheme, such as price. Then you simply go through the list and say, hey, if I had a fractional order, I'll round up if I stay within budget. Otherwise, I'll round down. Now, the ordering is important because, things higher up the list are more likely to get rounded up than rounded down because, if you're all the way at the bottom of the list, a lot of things have already been rounded up and taken up that available budget space. But one thing we did note is that while it did, make, large differences in terms of, wow, I wish I made that much money. Relative to the overall budgets, there were quite small differences between the ordering methods. So to conclude, so we have all this data that we feed into an optimizer and that gives us these ordering recommendations that are again for review by human committee. The process is repeatable. That was the main goal of this project. I would argue it's very interpretable. I know I've only, I'm, throwing this at you in about 20 minutes. But I will say, from working with our sponsors and so forth, a lot of the logic behind the constraints and the objective function has seems very interpretable to everyone involved. And it's comprehensive. It's got that big picture. It can look at the whole wholesale, items and, in the hundreds of thousands to millions potentially. We've blended kind of this classical optimization method of linear programming. That's one of, the oldest tricks in the book for those with optimization background. But we've kind of nicely paired it with this, modern statistical learning approach of hyperparameter tuning. And those come together to give us our nice little robot. And, the reason we want the linear programming and this sort of sequence of linear programs is we managed to avoid the computational complexity of integer programming for implementing some of these constraints. So, this is actually something that runs quite quickly. Even if you have tens of thousands of items, I would say, order 10 minutes to complete a run. So thank you, everyone. I will take questions, time permitting. Yeah, go ahead.
So you've said a couple of times, we trained this on historical data. I don't know how old your historical data is, but have you tested it by saying, let's say I've got 20 years of data. I'm going to train on 15 years of it and see how well it predicts the last 5 for which I've got truth data.
Yes. So one thing I will say is that when we look at the so it's usually used for comparing policies to each other. As to how, as to whether we can, match or use what the existing policy was to see if we can match that. That's really more evaluating wholesale. But I know there have been a lot of validation studies on wholesale done. For examining policies, yes, we can use a certain amount of training data and then see, how does it perform relative to, finances and so forth during, a 5-year period that we treat as the future, even though it already happened. Generally, though, what we've been doing is we've been looking at the different policies. There are a lot of assumptions that go into wholesale. It's a discrete event simulator. So there are going to be some, for computational tractability, there are going to be some simplifications that make it reflect reality less. But from what I've seen generally, it's as far as indicating finances, I think I recall it does quite well. Did I answer your question? Or yeah. I feel yeah.
I look at this from a modeling simulation point of view. Validation, how well does it work? You're looking for ways to test it. And I'm saying, if you're modeling actual historical data, you've got that opportunity to do that.
Yeah, I will say that the so if we use so maybe this relates more to the hyperparameters. So how good are the hyperparameters? I will say that the hyperparameter values that we got from training on historical data perform the best. Compared to any other value we could come up with. It also happened to approximate what the subject matter experts came with. But yeah, as far as validation, it was really just kind of comparing to baseline heuristic approaches to see which perform better. But it's still all within the frame. We can only evaluate it using wholesale in order to, I guess, make it an apples to apples comparison. Yes.
Can you go back to that slide that have the different radar frontiers, I guess, or
Yes. Yeah. Whoops.
Yeah, understanding this, I don't understand why they're not monotonic.
Yeah, I will say it's each of the points is a point estimate. But as you increase the sample size, it would probably become more monotonic. I think this was more just kind of the variation reflected in the point estimates.
It's also a strange jump from the yellow down to the red, where is there any explanation for why it shifts so much?
Yeah, that is a good observation. So at a certain point, you're when you go from yellow to red, for example, you're changing the threshold for what you value how you value a back order. Because it's profit increase versus back order reduction. So I think a lot of it has to do with just like there were a lot of items that, you know, once you cross that threshold, a lot of items got categorized into the, hey, we should go ahead and buy them. There was like an acceptable profit loss relative to the back order reduction value. Yes.
You said that this is doing tens of thousands of items. Is there any accounting for relationships between items? You know, I know I need to order a new airbag for my car, and that means I also need the associated bolts and wiring harness.
Yeah, so I guess that's more related to like the demand signals. Is there some sort of any correlation we consider? So for this, we really this was almost like a steady state, you know, items independent for the demand signals. We do have ongoing research in, you know, predicting demand, but you know, predicting demand for items is like predicting, you know, stock prices in the stock market. So it's
I mean, like, if you think about it, an item could be a kit, right? So if it's always the same set of bolts or brackets or whatever,
Right.
that item could be that set as well.
Yes, that is a very difficult and ongoing area of research.
So what about if you had new items on the list? How does this look?
Yes, so new items on the list, so those are generally not going to have any demand history, right? So that is another open question that we're investigating. How do we, you know, predict what I guess demand distribution we expect these items to come from? So, you know, one possibility is to, you know, is it like the newest version of an old item? Maybe the old item's, you know, demand signal is representative of that. And that's, again, you know, that may be completely different. It's like, I think it's, you know, Columbia is coming out soon. Can we use, I think it's the Ohio that they're replacing. Can we use Ohio parts to, you know, predict, you know, demands for the Columbia parts? So difficult question, but yes, we're looking into that. Yes.
It may also be worth mentioning that we aren't calculating any of the raw metrics go into this. We can, we might like to, but the goal here is that this technique is supposed to slot seamlessly into our sponsor's data system. They calculate demand rates, they calculate lead times and prices and everything. We have our own opinions. Sometimes they're close, sometimes they're not. They're not important. The goal is to take the system they've got, have a plug and play module that says you plug in your numbers, turn the crank, here's a repeatable process. So there's a lot of interaction effects and special cases we would like to account for that their system doesn't, at least not yet. So that would be an area of future research. The goal here really is to take the numbers, whatever they are, and to come up with a kind of, you know, minimum B- approach, maybe better, but like this will do. If you follow these rules, you cannot make huge mistakes unless the data are fundamentally worked. If the data are right, the recommendations will be decent, maybe even quite good.
I guess we're out of time. Thank you, everyone.